Have you ever written identical code for different data types, leading to frustrating duplication? C Sharp offers a powerful solution. It enables flexible, reusable code, simplifying maintenance and enhancing adaptability across your projects. This elegant solution is C Sharp generics. They allow you to design classes and methods with type placeholders, deferring type specification until instantiation. You write a single piece of code that works with various data types, adapting dynamically, like a versatile template. Generics offer significant benefits. They enable extensive code reuse, allowing a single algorithm or data structure to operate on any data type, eliminating redundant code. They also ensure strong type safety, catching type mismatches at compile time, preventing runtime errors. Our exploration begins with generic methods. Traditionally, performing the same operation on different data types required multiple overloaded methods. Generic methods elegantly solve this by allowing a single method signature to operate on various data types, reducing code duplication and simplifying your code base. The syntax for a generic method is distinct. It involves specifying a type parameter, conventionally T for type, within angle brackets, like T, immediately after the method name. This T acts as a placeholder, signaling that the method is designed to be generic and adaptable. This T is a symbolic placeholder representing any type. When you call the generic method, you explicitly or implicitly define what actual data type T should represent. T could be an integer, string, or custom class, making the method incredibly versatile and type-safe. Let's consider a swap method. Without generics, you'd need separate methods for swapping integers, strings, and every other data type. This leads to repetitive, verbose code that is cumbersome to write and difficult to maintain. Each new type would necessitate another identical method. With generics, we can create a single swap T method that works universally. By defining T as a type parameter, this one method can swap variables of any data type, like integers, strings, or custom objects. This eliminates multiple implementations, showcasing generics efficiency. In our generic swap T method, T is a type parameter, a flexible placeholder. When swap is called, the C# compiler infers or you explicitly specify the actual data type T represents. This type substitution occurs at compile time, ensuring strong type safety. To demonstrate our generic swap T method, let's first observe it in action with integer values. This will clearly illustrate how the method, despite its generic definition, seamlessly handles concrete numerical data. It performs the swap operation effectively. Consider two integer variables, number 1 initialized to 5 and number 2 to 10. Upon executing the generic swap method, their values are precisely exchanged. Number 1 will then hold 10 and number 2 will hold 5, demonstrating the method's successful and type-safe operation. Having seen swap T operate on integers, let's now extend our observation to strings. We will use the exact same generic swap T method definition without modifications to handle string values. This illustrates generic's core principle, writing code once and reusing it across diverse types. Imagine two string variables, str1 containing hello and str2 holding world. When our generic swap method is called, it performs its intended function. Consequently, str1 will then contain world and str2 will contain hello, perfectly demonstrating the method's ability to swap string contents. This demonstration clearly highlights the immense power of generic methods. A single, unified implementation effectively handles operations across a multitude of data types. This drastically reduces repetitive code, simplifies development, minimizes errors, and significantly improves maintainability and scalability of your C# applications. Building on generic methods, we now explore generic classes. This concept extends generics to entire classes, allowing you to define class structures with type parameters. The entire class can adapt to specific data types it needs to manage, enabling highly adaptable data structures and components, enhancing code reusability. A generic class is a blueprint where types are not fixed until an object is created. By incorporating type parameters like T, a generic class becomes incredibly versatile. It can be instantiated to work with any specific data type, whether integer, string, or custom object, all while maintaining strong type safety. The syntax for defining a generic class closely mirrors that of a generic method. The type parameter, commonly t, is placed within angle brackets immediately following the class name. This clear notation signals that the class is generic, ready to be specialized with concrete types upon instantiation. To illustrate generic classes, let's create a simple data store T class. Its purpose is to encapsulate and manage a single item of data. The generic design means this item can be of any type, determined by T specified during instantiation. This makes data store T highly adaptable. Within our data store T class, we define a property named data with the type T. This means data is not restricted to a single predefined type. It can flexibly hold an integer, string, Boolean, or any custom object, depending on how data store is instantiated, showcasing core generic flexibility. The power of a generic class is realized when we create an instance. We explicitly specify the actual data type, T, should represent at instantiation. This declaration tells the compiler precisely what kind of data this instance will handle, ensuring type safety from the outset and preventing type-related errors. For example, data store string store equals new data store string creates an instance named string store. This object is now exclusively typed for string data. Any attempt to store a non-string value into its data property would result in a compile time error demonstrating robust type safety. Once our string store instance is created and typed for strings, we can assign a string value to its data property without issues. For instance, string store data equals generic example is valid. The compiler understands data expects a string, ensuring error-free data handling. Following the same pattern, we can demonstrate data store T's versatility by creating another instance, tailored for integer values. This involves declaring data store int instore equals new data store int. The only change is the type argument, transforming this new instance to handle numerical data exclusively. With data store int instore, this new instance exclusively manages integer data. T is resolved to int. Its data property will only accept integer values, and any attempt to assign a non-integer type will be flagged as a compile time error, reinforcing strong type checking. Just as with our string example, we can confidently assign an integer value to the data property of our instore instance. An assignment like intstore data equals 123 executes flawlessly. The compiler verifies 123 is an integer, matching the int type, ensuring type consistency. Generic classes are indispensable for building robust and flexible data structures. Common collections like list, T, or dictionary, T-key, T-value, are generic. They allow you to store and manage elements of any specified type, from primitives to complex objects, while rigorously enforcing type safety. This prevents accidental type mixing and ensures predictable behavior. Having explored generic methods and classes, we now move to type constraints. While generics offer flexibility, sometimes you need to impose restrictions on the types used. Type constraints provide this crucial mechanism, adding control and safety. They allow you to define more specialized and robust generic implementations. There are scenarios where your generic method or class needs T to possess specific capabilities. For instance, you might need to call a method on T, ensure T can be instantiated with a default constructor, or confirm T is a reference type. Simply allowing any type for T is insufficient, as it could lead to runtime errors. Type constraints are invaluable for specifying requirements for type arguments. By adding a constraint, you declare, this generic type T must be a class, implement this interface, or have a parameterless constructor. This restriction ensures only types meeting these criteria can be used, preventing invalid operations. A frequently used constraint is where T, class. This dictates that any type argument for T must be a reference type. T cannot be a value type like an integer or struct. It must refer to an object on the heap, such as a class, interface, delegate, or array. This constraint is vital for reference type operations. When where T, class is applied, T is limited to representing classes, interfaces, delegates, or array types. It strictly excludes value types like int or struct. Therefore, types such as int, double, bool, or any struct cannot be used as arguments for T when this constraint is present, ensuring type compatibility. The where T class constraint is powerful for generic code interacting with reference type characteristics. A prime example is performing a null check. Only reference types can genuinely be null. By applying this constraint, you ensure T is a type for which a null check is meaningful and valid, preventing logical errors. Omitting where T class and then attempting a null check on a value type T would result in a compile time error. The C# compiler understands that value types cannot be null, making such an operation invalid. The constraint acts as a safeguard, guiding you to write correct and type-safe generic code. By adding the where T class constraint, you empower the C# compiler to enforce type correctness at compile time. This guarantees that only types compatible with reference type operations are used. The result is a significant reduction in potential runtime errors, leading to more stable and robust applications. In summary, we've explored 3 core C# generics concepts. Generic methods enable flexible function design, allowing a single method to operate on diverse data types. Generic classes provide reusable and type-safe data structures. Type constraints enforce specific rules and capabilities on generic type parameters, enhancing control and safety. As a best practice, use descriptive names for your generic type parameters to enhance readability. While T is common, for complex scenarios, consider names like T-key and T-value for a generic dictionary or T-item for a generic list. Such naming conventions make your generic code much easier to understand and maintain. While we focused on where T class, C# offers other useful constraints. Where T struct restricts T to be a value type. Where T new requires T to have a public parameterless constructor. Interface constraints, like where T comparable T, ensure T implements a specific interface. Mastering C# generics is crucial for becoming a proficient developer. By embracing generic methods, classes, and type constraints, you will write code that is more powerful, efficient, and adaptable. This leads to cleaner, more robust, and significantly more maintainable applications, ultimately enhancing your productivity and software quality.